Hello, today is all about drawing graphs, or more accurately sketches, of the derivatives or the slope function. So our dy dx, we've been saying for ages, is a function that gives us the slopes of the tangents to the curve at different values of x. Well, that means it is a function and it has a graph just like any other function. And our task today is going to be getting good at interpreting and sketching those derivative functions, and this should help us with our intuition as to how functions are changing as x changes. So that's the underlying purpose, and let's get into some questions. We're going to do a few examples. We're going to switch to Geogebra and see how the graphs of those functions, when accurately drawn out, play out, and we're going to do that first. Then we're going to look at how, if we have functions to begin with, how would we draw it? How would we figure out what their derivative function should look like? So, first question, y is equal to 3x minus 2. What's the derivative? Dy dx is just going to be 3. So if we wanted to draw a graph of that, it would be y equals 3. So the graph of this function would be y equals 3. Let's have a quick look at this on Geogebra. The screen is about to get brighter. So we have our function, f of x is equal to 3x minus 2, which was the function that we started with. And that is our purple line here. I'm going to move this over a little bit so we can see it a touch easier. And then we are, our derivative function, if we graphed it, would be y is equal to 3. So dy dx was 3. If we graph it, it's y is equal to 3, which is a constant function, and where y is always equal to 3. That's our straight line going across here. So we can pause this so you can draw a sketch of it if you would find it useful for your notes. So the slope of this line is effectively what we have graphed here, y equals 3. Now if we take a quadratic function here, we get dy dx would be 2x minus 2. We end up with a linear function. So y would be, if we graph this, it would be y is equal to 2x minus 2. So let's go back to Geogebra and have a look at that. So we have y is equal to x squared minus 2x minus 3 is our grey function here. It's a positive quadratic, so it looks like a smiley face. And then if we plot our derivative function, dy dx is equal to 2x minus 2, we end up with a straight line. But the key thing we have to spot here is what is the root of this equation? Y is equal to 2x minus 2. Well, that's going to be where dy dx is equal to 0. And this is our key point that we need to recognize. The minimum point in our quadratic is where dy dx is equal to 0. We're effectively finding the root of the derivative function. So when we set dy dx equal to 0, we are finding the root of our derivative function. We're finding the location of the maximum or minimum of our original function. We're also finding the root of our derivative function, the function that we've got here. So that is where our x-axis crossing is going to occur. Switching to our cubic. We have y, so dy dx is equal to 3x squared minus 3. Where is that going to have its maximum and minimum points? Let's just find them and then see if we get the correct values. So we'd be looking for where that is equal to 0. So we would have 3 on x squared minus 1 is equal to 0. Divide both sides by 3. And either by difference of two squares, either by difference of two squares, difference of two squares, or by getting 1 by itself and then getting plus or minus the square root of 1, we will get that x is equal to 1 and x is equal to minus 1 are the roots of our dy dx. They should be the turning points of our original cubic. So let's see if that's what happens in practice. So we have our cubic here, our brown or orange type function, and its derivative is 3x squared minus 3. And I'm expecting the roots of my grey quadratic to be the same as the maximum and minimum point of my cubic, and I can see that it is. I can also see that the point of inflection of my cubic is the minimum point of my quadratic, which makes sense because if I get the derivative of my grey function of my dy dx, I get the 2y dx squared is going to be where I get the minimum there, and that is going to be the point of inflection of the original function. So the point of inflection should give us the minimum, and then the roots should be given to us by the maximum and minimum point of the original function. So this is how we can start to build a picture of what's going on. Again, if we look at the fact that this is the slope function, if we look here when we're coming to our slope becoming, our slope function is returning positive values, so our grey line is above the x-axis up until we get to the maximum point. Then our slope is negative until we get to the minimum point, and then it is positive again past that point. So our grey line returns the values for our slope. Now let's have a look at sine and cosine. If we have y is equal to sine x, what's dy dx? It's just equal to cosine of x. Let's have a look at this in practice and see if we can build some intuition as to why that should be the case. So I have my green line is my sine function, and if I plot my cosine function, I have plotted cos of x minus 2 so that the two functions aren't overlapping each other to try and make them easier to read. But if we look at what's happening here with our function, this is our midline, so this is our effectively 0 line here. And if we look at where our derivative, if we look at where our original function sine x would have its derivative equal to 0. So dy dx would be equal to 0 at the top of our hill at the maximum point here. And that is where we are having the root of our cosine function. So this is where we have our turning point of our original function gives us the root of the other function. I move this over a little bit, where I have another turning point here. I drop down and I'm at another root of my cosine function. So I can see that the same rule applies for sine and cosine, and it is a perfectly reasonable thing that the examiners could ask you to justify why it is that sine and cosine are derivatives of each other. So if we look at the general shape of sine, its slope starts out positive and tends toward 0, starts positive, tends towards 0, then it is negative, comes to a point of inflection, and what would we expect to happen at a point of inflection? We'd expect to have a minimum. We would expect to have our d2y dx squared equal to 0. So we would have the min or max point of our derivative function would be in line with the point of inflection of our original function. Then if we go around to where the minimum, or one of the minimums of our sine function and r is, we end up at the root of our cosine function. So again, this is a visual argument for why sine, the derivative of sine, is cosine. Now, let's go through a few examples of how to do this in practice. So if I start out with a straight line graph, my blue line here crosses the y-axis at -1, crosses the x-axis at 3. What is the slope of this line? Well, it's just going to be m is equal to rise over run. So my dy dx is my slope. So I rise by 1 and run across by 3. So rise over run. My slope is 1/3. So my derivative function would be, if I draw in my axes, let's say that this is 1 and 1/3 is about there and 2/3 would be about there. So my derivative function would just be a constant going straight across at y is 1/3. I'm going to redraw that straighter. Now, that's a little neater. So this is going to be the graph of, or the sketch of, my derivative function, and where y is equal to 1/3. So all of the y values along my blue line are 1/3. So that's the definition of that line. For a quadratic, we don't know the slope, but we do know here we have a negative slope, and then at x is equal to 5, we have a minimum, and here we have a positive slope. Well, that means that this is a positive quadratic, so I'm going to end up with a straight line function, I know. So I have x is equal to 5 on my x-axis. That's going to be the root of my function. I know before x is equal to 5, I have a negative slope, and after I have a positive one. So I'm going to have a straight line function that looks something like that. Next I have, this is a cubic, but what type of cubic is it? Well, as x gets larger, my tail goes downward. So this is a negative cubic, so I'm going to end up with a negative quadratic derivative. And I know that its root should be at the minimum and maximum point, and its own minimum or maximum should be at the point of inflection. So let's draw in 1, 2, and 3. 1, 2, 3. So I know that my slope should be, negative to here. So it should be negative coming down to 1. Pardon, my slope function should be negative to 1. So I should be below the x-axis up to 1. Then I am positive all the way around. I should have my maximum at the point of inflection at 2. And then I should be negative once I get past x is equal to 3. So remember that the y outputs of this blue line are my derivative. So when its y outputs would be negative, dy dx is negative, or f dash x. Now, finally, what type of function is this, and what does its derivative look like? I should know that this looks like an exponential function. And what do I know about the derivative of an exponential function? It's the same thing. If I have y is equal to e to the x, its derivative is just what dy dx is equal to e to the x. So I would end up with something that is basically the same shape.